Good morning. I'm happy to present to you our paper on color-based fusion of MRI modalities for brain tumor segmentation. This is Nachwa Aboubakr, and this work has been done in collaboration with Aboubakr and Professor James Crowley. Competent diagnosis of MRI imagery requires years of experience. MRI imaging, in particular, are difficult to interpret, as an accurate diagnosis can require adjustment of a number of parameters and the exploration of different MRI modalities. The automatic segmentation of MRI images offer a unique set of challenges. Pixels in each 2D image need to be considered as a part of a 3D volume, as neighborhooding voxels provide contextual information that can be important for the interpretation. This information can be lost when processing each slice independently. For that, some approaches to MRI segmentation uses the whole 3D volume for segmentation using 3D convolutions. These approaches require training large models as well as considerable computational power and training data to converge. On the other hand, approaches that consider slice-by-slice segmentation of pathologies are more affordable in terms of model size and the number of parameters. However, these approaches they tend to ignore contextual information from 3D voxels, and this generally comes at the cost of reduction of performance. To overcome the limitations of 2D approaches, several works have investigated ideas to transform the 3D MRI volume into 2D while keeping some kind of contextual information. These techniques consider a 3D transformation of the MRI volume to 2D image, use the 2D images for segmentation, then reconstruct the final segmented 3D volume from multiple views. 3D transformation approaches include the use of multiple planes from different angles of an MRI image, and also other approaches like projection-based techniques that project from a 3D volume to 2D, use the 2D for segmentation, and then back project the segmentation to segmentation masks to 3D volume. We find these type of approaches are very promising as they have a comparable model size to slice-by-slice approaches, and in functionality are comparable to 3D volume segmentation. However, they are still far in performance from approaches that consider the whole 3D volume as a 3D unit. For that, in this work, our objective is to improve transformation-based methods and find a trade-off between quality of the segmentation and the computational complexity needed for the segmentation of pathologies in MRI. To do that, we first investigate the use of different MRI modalities and propose a method to fuse them in the color space. And second, we improve the network structure of a recent projection-based method and demonstrate our model structure choices in an ablation study. Different MRI modalities illustrate different information, and those can be useful for the segmentation. For example, T1 shows healthy tissues with high intensity and the pathology with low intensity. T2, on the other hand, illustrate the pathology with a high intensity response. With T1 with a contrasting agent, the tumor border can be visually distinguishable by the bright signal of the accumulated contrast agent. In flare modality, signal of the water molecules are suppressed, which helps in distinguishing edema region. Works that studied the fusion of medical imagery modalities either fuse the modality at the input level or inside the network at the layer level or at the end in the decision phase. To exploit this information exists in different MRI modalities. We study the fusion of these modalities at the input level by stacking different modalities on the color channels. Then we convert the stacked images from a specific color space to RGB using color space conversion formulas. we compare between different color spaces, namely RGB, XYZ, HSV, and LAP, taking the segmentation of tumor in brain MRI images as a use case. We consider the following MRI modalities in this order: FLAIR to be in the first channel, T1 with GAD in the second channel, and lastly T2. Here we can see three slices of three different MRI modalities. By only stacking them on the color channel, we can get a visually appealing RGB image. And by converting this image into other color spaces, we get these other images. To evaluate this idea of color fusion with a projection-based pipeline of MRI segmentation, we develop a similar structure to a previous work of Angerman and Haltmir. Starting from an MRI image volume, we use the maximum intensity projection to get projected images at different angles from on the axial plane. Here is an example of the maximum intensity projected images. Then we fuse these 2D images on different modalities using different color spaces. The resulted set of 2D images are then passed to our model. The backbone of our model is a standard unit, 2D unit, that's randomly initialized. The model receives a color fused 2D projected images extracted from the MRI volume of different modalities. The output of unit is then used to reconstruct the volume using linear reconstruction where a voxel value in the this tensor is defined as the sum over the corresponding 2D projected values. Then we follow with denoising the segmentation with average pooling, layer, and instant normalization. For training, we use a joint loss function of dice loss and cross entropy loss with equal contribution. For our experiment, we use the BRATS data set from Mekai Medical Imaging Decathlon. And we consider for our experiment two classes only, the pathology, which includes enhanced and non-enhanced tumor, and the background class, which includes the edema and the background labels. For the evaluation, we use 4 metric: DICE score, intersection over union, precision, and recall. We evaluate our model on 4 different networks: a standard 2D unit, which learns to segment the MRI volume on slice-by-slice basis; a 3D unit, which on the opposite uses the 3D convolution to segment the 3D volume; and 2 other transformation-based techniques, namely projection unit and the 2.5D unit, that are comparable in the architecture to our model. And from this table, we can see that our model scores second after 3D unit with around half the number of training parameters. Our model outperforms the other methods with large margin while preserving model complexity. Here we report on the performance of our model for each modality separately, and then using a color fusion. From this table, we can see a significant improvement using modality fusion with the color spaces. And from these HSV hue saturation value color space stands out and performs the best on most metric. Here we can see the effect of our different model choices of our network, starting from the model that proposed by Angerman and Haltmir. We re-implemented the model and tested it using different MRI modalities. We can see the results here. And then we report on the effect of each modification we made on the network over their model. I invite you to read the paper for more details and for the link of the implementation code. So to conclude, we presented a method to fuse multiple MRI modalities that uses color space transformation. We showed that this fusion improves the results of segmentation significantly with no significant additional computation. And we proposed improvement of a recent projection-based segmentation network and showed an ablation study to demonstrate the effect of our choices. And our model outperforms the previous projection-based network with more than 12 points while preserving the same model complexity and training parameters. Thank you for listening.